Hi. In this course we're going to use a fair amount of calculus and specifically integration. So I want to take a moment just to go through the basic notion of what integration actually is. And in this video I'm going to use an example that you're all familiar with from your earlier physics course on mechanics. In the follow-up video, part 2, I'm going to use an example from electrostatics, stuff we are studying right now. So here's what integration is. Integration at a fundamental level is a sum. You're summing up lots and lots of parts, but each single part is absolutely tiny. If you take that to its logical extreme, essentially you have infinitely many parts, but each part contributes an infinitesimally small amount to the final sum. That's what I try to spell out here on this paper. Right? You sum up lots and lots of teeny tiny bits. And by lots and lots, I mean infinitely many, but each one is infinitesimally small, which gives it a chance to, in the end, come out to be a finite number. So let's start with the following example that I've pre-drawn here for you. Right, so think back to kinematics. Let's imagine you've got the following velocity time graph. Right, so maybe you could imagine it's a car or something that's going along the highway. There's a certain velocity here. Everything is positive. Velocity, some value, v0. And then it's slowing down until it reaches 0. And the function that describes this shape, well, it's not going to be a straight line, right? In your kinematics, the kinematics section of your first physics course, you probably spent most of the time dealing with cases where there was constant acceleration, where the velocity versus time graph was a straight line. Well, here this is not the case, right? So here the velocity as a function of time is given by, say, this function here, v0 minus ct squared. So when t equals 0, this thing isn't there, and we add v0, and then after some time, let's call it t stop, the velocity itself is 0, and that's when we stop. Now it doesn't take much to figure out what this value is. We can find that t stop is going to be equal to the square root of v0 over c. That constant here, some arbitrary constant, right? Because then if I plug this back in here, it gets squared, the c will cancel, and v0 minus v0, yes, that is 0. Okay, so I want to find the total displacement between time equals 0 and the stopping time, and while I'm going to use the, symbolic t stop, I know what that is in terms of my function. So you look at this and you're like, I don't know what to do here. Right? The velocity is changing. If it were a constant velocity, I would know what to do. If it were a constant velocity, I'd just say distance traveled is velocity times time, because that is what velocity is defined as. How far do you go per second? So you travel for 3 seconds, well, it's 3 times the velocity value, that's how far you've gone. But here the velocity is not constant, so how do I deal with this? Well, if you think about it, what you're going to end up the idea you might come up with is, let me just approximate this function by a bunch of constant velocities. So you might say, maybe for the first fraction of a second, I'm going at this speed. Then for the next fraction of a second, or maybe the next second, I'm going at this speed. The next fraction of a second, I'm going at this speed. Then I'm going to go at this speed. Right, so you split up your total time into a bunch of tiny steps. Something like this. Now you know that if this is a car, right? You know that your car is not actually going this speed for 1 second, and then this other speed for the next second, and then this speed for the next second, with sort of jumps in between. But you realize, hey, that's actually a pretty good approximation. So if I can find the total distance traveled by this step function, or by an object, hypothetical object, that whose velocity is described by the step function, that's going to be a pretty good approximation to the actual distance traveled. And for each one, you then know that the distance traveled here is just the velocity, how fast we're going, times the time for which you were going that far. So let's call this time interval delta t. So we're going v naught times delta t. And graphically, v naught, that's the height, delta t is the width, right? That just gives you the area of this, this rectangle here. And the same is true for the next step, right? Here, you're going a bit more slowly. Your velocity is not v naught, it's v naught minus a little bit. So you just read off what is the velocity at this time where this column is located. And you multiply that velocity, right, that's the height of the column, by the width, which is again delta t. This is another delta t. And so you add them all up, because the total displacement is the sum of the individual displacements. And the conclusion you come to is that the total distance traveled is really just the area under your curve, right? That's something you hopefully remember, and this is the justification for it, right? We can split this up into chunks, and if you want to be more accurate, well, we didn't make our chunks smaller. Maybe we take it not to be 1 second, but 0.1 second, or 100th of a second, or 1/1000th of a second. So, what is the total distance traveled? That's our goal. So let's write down my total displacement, delta x. I said distance traveled, I mean displacement, but in this case here, where everything is positive, those come to be the same thing. Delta x, the displacement, is equal to, well, the first chunk, right? Delta t, let's call this chunk, let's call this time at which this happens, t1. So I'm going to squeeze this in here, right? This is the time t1. The width of this is delta t. This is time t2. This is time t3. This is time t4, and so on. Right. So the total distance traveled is going to be the width of this, delta t, times the velocity at this time, right, which you can read off the graph, v times t1. I add to that the second distance traveled during the second interval, delta t times v at the second time, plus the third chunk, and so on. But all the way up to the time when the time reaches t stop. So really, the way I might write this down is that I'm saying I want to take the sum of delta t times v, let's call it t subscript I as a kind of index, for all I. Alright, so I'm summing up all the values of I, well, up to t stop. And if I want to make those intervals infinitesimally small, right, it's not a millionth, not a billionth of a second, but infinitely small, we call this infinitesimally small, then this is rewritten in a different form So this becomes, as I say that delta t gets to be tiny, gets to approach 0, this becomes, well, I'm writing this down. This is just, in a sense, a notation I'm introducing as this, with this big sort of long S shape for sum. Of course, you know this is the integral sign of dt v of t. The delta t becomes a dt, same thing, just a notation. Mathematicians have at some point decided that as delta t actually becomes, approaches 0, I'm going to replace the Greek delta with a Latin d. Okay, why not? Right? It's just a notational thing. It helps us differentiate between small finite and infinitesimally small quantities. Now, this sum, right, is what is the sum taking over? How do I know what terms to add? Well, here I just said for all I, but now I have an infinite number of them. I can't really count to infinity. I'm not that kind of infinity anyway. So I'm just going to say, I'm going to do this, and I'm going to start at the beginning. I'll write this down here. And I'm going to go to the time. I'm going to stop summing once I reach this time here. At t equals t subscript stop. So that is just notation. Of course, you recognize that notation from your calculus course, right? But really, I'm just introducing this notation as a way to write a sum over an infinite number of tiny chunks. Okay. Now, right here it is. Here's where we got to. You know how to evaluate an integral. So let's do that first, and then we can go back and think about why are the rules of integration the ones that you know, right? Why is this thing here that I just said this is a different way of writing a sum? Why can I evaluate this, work out what the sum actually comes to with the rules that you know? But let's first do it, then worry about the why. So my delta x is equal to the integral, meaning the sum, and I'm going to abbreviate a little bit. I'm just going to write 0 instead of t equals 0 up to t stop of summing up the width of each tiny chunk times v of t. But remember, I've got an explicit expression here, this one here, right? I know what that is. So let me write that in. This is v naught, so some constant where I start, minus c t squared. And now we just use the rules of integration. I assume you know those. Right? You know those from your calculus course. So let's just work this out. This is going to be v naught times t minus 1/3 c t cubed evaluated between 0 and t stop. Of course, when I evaluate it at t stop, I just plug in t stop instead of t. When I plug in 0, though, I get nothing. So this is just equal to v naught times t stop minus 1/3 c t stop cubed. And again, I could plug in for t stop the value I found here if I want to express it all in terms of v naught and c. But it doesn't really matter, right? So that, in a sense, is our final answer. Now the question, kind of the cheating part here is, it didn't tell you why it is that just rewriting the sum in this form, that is really the integration that you know. And that really comes from what's called a fundamental theorem of calculus, which hopefully you remember from your calculus class. But just to give you the basics, right, what we have is that x at the end, let's call it t, I guess I call it t stop, let me stick with that, is equal to the sum, right, what I had up here, the sum of all the little chunks, or I can rewrite that as with this funny way, if my chunks are becoming infinitesimally small and I've got infinitely many of them. So that's equal to 0 to t, not t and t stop, excuse me, t stop, dt v of t. But I know that vt is dx dt in the first place. Right? How far are you traveling per time? How far are you going to travel in the next tiny fraction of a second? What's the change of your displacement? Right? That is the definition of v. So let me write like this. I guess it's a definition. It's equivalent to this. So you've got those two relationships. And so what that means is what we're really doing is we are asking what function x of t is such that when I differentiate it, I get back the v. And so you can check that indeed, right, this function, if I differentiate it with respect to t, or I guess that I'm changing t stop, you've got to be careful with your variables here. When I differentiate this function here, I get back the original v that I had before. Right? So we know those have to be the rules essentially because what those two things show is that whatever this operation is, this thing we call integration, well, we know what the relationship between those two is. We get from there to there by differentiating with respect to time. And so I know, no matter what kind of symbol I'm writing there, how those two are related. So I know I can find this from knowing this by essentially asking, well, what thing can I put here that makes this true? This is the very sort of rough and ready, dirty physicist version of the fundamental theorem of calculus. Don't show this to any mathematician. They'll have my head for sure. But it's not the point here, right? The point here is that you understand that integration fundamentally is taking a sum. And mechanically, in terms of the math that you're doing, when you actually work it out, is you're asking, well, what function, when I differentiate it, gives me back the thing that I want to integrate. So if you understand that basic idea that integration is a sum of infinitely many infinitesimally small parts, then we can now apply that to more interesting applications, such as ones we find in electrostatics. That's what I'm going to do in part 2 of this, I guess, 2-part video series.